So in the last lesson, what we looked at was the signed area under a curve, not the actual area under the curve, but the signed area. Today, what we're going to look at is the actual area, and that's for applied mathematicians, that's going to be the important thing because, if we can get a function to model, say, the shape of a garden bed, then what we can do is work out areas under a curve, and we're really interested in the physical area. If I said to a local gardening supplier that the signed area under a curve for a garden bed that I'd modelled was 0, so that's how much mulch I need, then obviously the garden place is going to ask me to leave fairly promptly. So for applied mathematics, we want the actual area, not the signed area. Okay, so just note that if we are finding the area, then all I do is I integrate f of x to get the antiderivative and then bang the terminals in. So it's just like the signed area, except we know that this will give us the physical or the actual area because we can see that this is what it is. Okay, it doesn't dip below the x-axis. So this is going to be both the signed area and the actual area. This function here goes below the x-axis, so if I integrate f of x between the terminals b and a without this negative sign, it'll give us the negative signed area. Now, if I'm talking about the positive, talking about physical areas, I would state it as a positive value. So all I do is I negate the negative signed area that this will produce, and I get a positive amount, okay, or I get the actual area. Now, an alternative to doing that is to actually do this technique here. This is flip the terminals. Okay, and that's what most of you will start to do once you know that you are going to get a negative signed area between B and A. All you do is you rewrite it with the terminals flipped, okay, and that will automatically negate it, okay. And finally, this one here. So what would you do to get the actual area of this function here? That is to get that and that. So the answer, the actual area, is not found by doing or integrating between b and a for f of x dx. This will not give you the actual area. Remember, this will give you the signed area, which in this case looks to be 0. Okay, so this one here will give you 0. And if I told you, can't you see that the area under this curve, or the area bound by the curve and the x-axis between b and a, is 0, you'd say, no, it's not. Like, there's stuff there and there's stuff there. And the only way to do this is to actually just split the integral. So what you do is you integrate between b and c, that's this part here, for f of x dx, and then you add the negative version of this one here. So C and A will give you, so if you integrate between C and A, that will give you the negative signed area, and then you drop a negative in front of the result. Alternatively, what you could do is go A equals integral BC f of x dx plus, and then you just flip the terminals of that. So plus AC, lower terminal, upper terminal, f of x dx. So it's important that you know how to do that. So I think I alluded to this last lesson where I said that if you want to find physical areas or actual areas under curves and you don't sketch the graph, you really are taking a risk of just throwing it into a flat out integral. So it says here, important, to find the area under a curve, you need, bolded, to sketch the graph first so that you can see which parts of the graph are under and which parts are over. You will also need the values of the x-intercepts for the terminals on the integrals. So you need to know where it cuts through the x-axis so you can pop them on the terminals here. Okay, so let's just try one. So find the area of the shaded region. So I need this part here and I need this part here. So I'm presuming that the x-intercept here is 2, but let's not presume that. What I'm going to do is just do this properly and say that the x-intercept occurs when y is equal to 0. X squared take away 4, 4 equals x squared, x equals plus or minus 2. So yep, it definitely is the case. All right, now let's use some function notation. So I'm going to say let f of x equal x squared take away 4. And let's write our integral statement out. Now this is where often in a VCAR exam you'll get 1 mark for just writing a statement like this. So the area is equal to. All right, I think the pen's a bit thin here, so I'm just going to go to a thicker. Okay, now, oh, that's a bit thick. Okay, I probably should have done this before I recorded. Medium thin. All right, we'll run with that. So I'm going to integrate between 4 and 2, f of x dx. That's going to give me this positive amount here. Now I'm going to add this part here, but I'm just going to flip the terminal so it's the lower first and the upper second. F of x dx. So the area is going to be found by doing this and then this. All right, so let's do it. A equals. All right, so this first one, what we need to get is an antiderivative of this. So when I integrate f of x for the independent variable x, I'm going to get x cubed over 3, take away 4x. So that's my first one. X cubed over 3, take away 4x, with the terminals 4 and 2, plus, now we're going to do that one there, which is x cubed over 3, take away 4x, 1, 2. Okay, so let's start evaluating this area here. Okay, so 4 is going to go in first, so that's going to be 64 on 3, take away 16, bracket that, take away 2 goes in, 8 on 3, take away 8, plus, okay, so now we need to do this part here, so 1 is going to go in, 1 over 3, take away 4, take away 2 goes in, which we already know is 8 on 3, take away 8. All right, so I tend to over bracket things here just to make sure I handle the negatives correctly. A equals. All right, so this is going to be 64 on 3, take away 16, 32, 42, 48 on 3, so just going to get them to equal parts. This one is going to be subtract, that's going to be 8 on 3, take away 24 on 3. This one is going to be 1/3, take away times 12 on 3. Take away this one here, which we already know, so let's just do this. It's 8 take away 24 is negative 16 on 3. All right, let's continue the fun over here. A equals. All right, so 64, 24, 16. So that's going to be 16 on 3. Take away this one here, so we're going to subtract what this result is, which means that we end up adding it. So that's plus 16 on 3. So that's subtract negative that. Yep, so that looks good. Plus, this is going to be negative 11 on 3 plus 16 on 3. Okay, so this is going to be 32 on 3, take away 11 on 3 plus 16 on 3. A equals 21, 31, 37. 37 on 3 units squared. I've got no idea whether I got that right, and to be honest with you, if I get it wrong, I'm going to redo this video anyway, but let's just find out. So, 4, 2, Remember, if it's a complicated function, define it and then use f of x, but this one's not too bad to type in. So there's the first part, and we're going to add 1 to x squared take 2, take 4, dx. All right, the moment of truth. That looks all right. Yay. Right, so there it is. There's no easy way to do that. So if you can find one, let me know. But otherwise, you just do it in as many parts as you need to get that area. All right, so let's go through a couple of old exam questions just to see how it's tested. All right, so the area enclosed by the graph of y equals that, the x-axis and the y-axis is given by one of these statements here. Okay, so the area, the actual area, not the signed area. Okay, so the first thing we need to do is probably sketch this thing here. So that's y equals negative e to the x plus 3 plus 1. So what that is, it's the e to the x function, which looks like this, and it is reflected, so it does that. It's shifted 3 units to the right, so like that y-intercept will just go lower, and then it goes up 1 unit. So it's going to look something like, I don't know, something like, I'm guessing, that. So the area that we'd be referring to would be, where's my highlighter? Would be this little bit in here, that part there. That's bound by the x and the y axes, or the area enclosed. Okay, so what I'm going to do is I need to work out that value there, and then I'm going to integrate between 0 and whatever that value is there to find this area here. I know that it's going to give me a negative signed area, so I'm going to negate the result. Okay, so essentially what I'll do is I'll go negative integrate 1 take e to the x plus 3 dx between, so the upper terminal will be 0 and the lower terminal will be whatever the x-intercept is. So let's get the x-intercept. It's when y is equal to 0. Negative 1 equals negative e to the x plus 3. That's 1 equals e to the x plus 3 log e1 equals x plus 3. Log e1 is 0, so x is equal to negative 3, which would make sense because e to the 0 will give us 1. So that x value is negative 3, so it's going to be a negative 3 there. All right, then what? So that's the answer. That'll give us the actual area, that space there. But that often isn't the answer, so what they'll often do is flip the terminals. What they've done, the answer is this one, and what they've done is this negative sign here, they've passed in inverted commas, so this is not correct maths talk here, but they've passed this negative sign back through the terms inside here, are the things that we're anti-diffing for. So they've actually rewritten it as 0, negative 3. Now this negative will negate the result of the negative signed areas to give it positive, but I can just pass that back in and rewrite this as e to the x plus 3. So I negate this thing and I negate the 1, which gives us negative 1 dx. So is that it? 0, negative 3. Yep, that's definitely it. So a tough problem there, even if you know your calculus and things like that. That one there is a great example of a multiple choice question that, yeah, you really need to sort of sketch this up and have a good think about how you're going to do it. Right, here's another good problem. The graph of the function y equals k cosine 3x, where k is an element of all real positives, is shown below. So the shaded area is 5 pi square units. Find the value of k. Okay, so the shaded area. So this is the total area, all right? Here's how I'm going to do this one. What I know is for this function here, let's just get this x-intercept here. And this area here, let's call this area 1, is the same as this area 2 and this area 3. So 3 lots of area 1 will be the total area, or 3 lots of area 1 will equal 5 pi. So what I intend to do is integrate between whatever this value here is and 0, and multiply the answer by 3, and then let it equal 5 pi, and that will give me the value of k. All right, here's how it's going to work. Now, I need to work out what the x-intercept is. So to do that, I'm just going to say that the period is 2 pi over 3, and the scale is 2 pi over 3, so it's this divided by 4, which is 2 pi over 12, which is pi on 6. So that's going to be pi on 6. This one here is going to be pi on 6. So pi on 6, 2 pi on 6, 3 pi on 6, 4 pi on 6, yeah. So 2 pi on 6, this one here is going to be 3 pi on 6, and this one here is going to be 4 pi on 6, or 2 pi on 3, which is the period. Yeah, of course. All right, so here is what I'm going to do. I'm going to say that the area is equal to 3 lots of the signed area between pi on 6 and 0 for k cosine 3x dx. Now for a 3-mark question, that's probably got us 1 mark, although I'd need to say what the area is. So I'm just going to put that in. The area we know is 5 pi. So that's 5 equals 3 times this again. So I probably should have written that in the first place, but doesn't matter. Okay, now what's going to happen is I'm just going to divide by 3 first of all. So 5 pi on 3 equals, this k is going to come out as well. K integrate pi on 6, 0 cosine 3x dx. Now let's integrate cosine 3x. So got my formula sheet here. You can hear it on the microphone hopefully, and I'm looking at the integration of cosine. Okay, and I can see here that when I integrate cosine I get positive sign, so it's going to be 5 pi on 3 equals k times square brackets, it's going to be 1 over 3 sine 3x, and the terminals are pi on 6 and 0. Now this thing here, that can come straight out, so that's going to be 5 pi on 3 equals k on 3. Now let's shove our terminals in. Sine of 3 multiplied by pi on 6 is pi on 2. Take away the sine of 0 goes in, the sine of, whoops, write that sine twice, the sine of 0. Okay, now when I multiply that by 3, that is just going to cancel out the k's times. All right, so sine of pi on 2, there it is up there, that's going to be 1. Take away sine of 0 is 0. 5 pi equals k. So k is actually 5 pi. Okay, so 5 pi. Doesn't seem right, but let's just check it out. Okay, so what I'll do is I'll integrate between shift 0, pi on 6, and 0 for the alleged k value, 5 pi, times cosine 3x dx. Now what that will do is give us this area here, and when I multiply that by 3, whoopsie, when I multiply that by 3, I should get 5 pi as an answer, and I do. All right, now again, really important to note that if I actually do an integral between this value here and this, so this is 3 pi on 6 or pi on 2, you might think, oh, why don't you just do that, Mr. Miller? Like, why are you messing around with this part's in 3 lots? So I'll just go from there to there. Now remember, so I'm going to do that, 3 pi on 6, and the answer actually will be negative. Okay, negative 5 pi on 3, because remember, integral calculus doesn't know what's where and things like that. So all it does basically is gives you this area here, which will be a negative signed area, and it will add this positive signed area to it. It doesn't know what's going on. It doesn't know what's above. Well, I suppose it does know, but you, the human, need to know what's where. Okay, and if you wanted to actually piece it all together, you'd have to do it as this first part of the integral here, and then negate this part here. Okay, so what I'm going to do is just do just that. So I'll go from smaller terminal, which is shift 0 pi on 6, up to the upper terminal, which is 3 pi on 6, or shift pi on 2 for 5, shift 0 times cosine 3x dx, and the answer to this just has to be 5 pi. Okay, so you can see there what I've done is just done the integral in 2 parts, this part here, and negated the result, and then added this part to it. So again, part of your mathematics homework should be really playtime. It should be involving yourself in a bit of mathematical play with these problems. Okay, so this example is one that's taken or lifted straight out of the book, and it's a technique that's used, or we can use in maths methods. It's not officially on the curriculum, but it's one that will come in handy, and we will use it at some point. So in the figure, the graph of y squared equals 9, 1 take x is shown. Okay, so that's this graph here. It's not a function, it is a relation. And the first thing they want us to do is find the coordinates of A and B. Okay, so they want us to find that point there and that point there. So this point here is the y-intercept, which occurs when x is equal to 0. So we've got y squared equals 9, 1 take 0, y squared equals 9, y equals plus minus 3. So that's 0, positive 3. This will be 0, negative 3. Now, this point here is going to be the x-intercept, which occurs when y is equal to 0. So 0 equals 9, 1 take x. 0 divided by 9, 1 take x. X is equal to 1. 1, 0. Okay, so find the exact area of the shaded region by evaluating this thing here. So they want us to get this shaded region here by evaluating this. Why this? What the hell is dy? Okay, well what they're doing is that we're integrating on y, not x. We're integrating for the independent variable y. Now at the moment we've got y, well, almost as the subject. To integrate on y, or to have the independent variable being y, we need to solve this thing for x. So I'm going to do that. So I've got y squared equals 9, 1 take x. Now, so I need to make x the subject, so it's going to be y squared over 9, take away 1 equals negative x. X is, funnily enough, 1 take y squared over 9, which is just what this is here. So what I'm going to do is just integrate this between a suitable value or for a suitable value of b to get the area. So what I'm essentially going to do then is integrate that, okay? But the value for b, what I want to do is find out the area from there to there on the y-axis. Right, so the suitable value for b is going to be 3. All right, so let's do it. So I'm going to set up my antiderivative. Now, the antiderivative of 1, we'd usually say it's x, but remember our independent variable is y, so it's going to be y. Take away, this goes up by 1, y to the 3 over 3, which is going to be y to the 3 over 27, between 3 and 0. Okay, 3 goes in first, so that's going to be 3, take away, 3 cubed is 27, 27 over 27 is 1, take away, 0, take away, 0, 2. And that is the exact area, it's 2 units squared. All right, so what we've just done is what's called integrating on y. Now you don't have to do that, we could integrate on x as well. So this function here, you'll note, is just the square root function, okay, this top half here. So we could actually state this as y equals the square root and the positive version of the square root of 9, 1 take x. And that would be the square root of 9 take away 9x. All right, so what we would then do is attempt to integrate this thing here, which would be y equals 9 take 9x to the half, okay? And I'll just show you. So let's just call y g of x for argument's sake. So if I integrate between this value here, which is 1 and 0, g of x dx, it should be exactly the same as integrating on y. The only thing is, it's a lot more complicated an integral to actually do. Okay? It should give us exactly the same answer. Let's see if it does. So we're going to go 1 and 0. G of x is 9 take 9x dx. To the half, you bonehead. 2. Okay, there you go. So we got exactly the same answer. All right, so there it is.